Hello everyone, welcome back to my channel. This is K.A. Priya of 4th semester studying in Sriventeshwara College of Engineering in Department of CSE, and today I am here to discuss about asymptotic notations. And the contents are introduction, big O notation, omega notation, theta notation, common asymptotic functions, best case, worst case, average case, practical applications, limitations and conclusion. Firstly, let me give the brief introduction of this topic. Welcome to my presentation on asymptotic notation, a fundamental concept in computer science that describes the performance of algorithms. Asymptotic notations allows us to analyze and compare different algorithms based on their time complexity, which is crucial for optimizing and improving their performance. In this presentation, we will introduce you to the three main types of asymptotic notations, that is big O, omega and theta. We will also discuss common asymptotic functions and their growth rates, as well as the difference between best case, worst case and average case time complexity. Finally, we will explore practical applications of asymptotic notations in computer science and their limitations. First, let us discuss about big O notation. Big O notation is a mathematical notation used to describe the upper bound of an algorithm's time complexity. It is commonly used in computer science to analyze and compare the efficiency of different algorithms. The notation is represented as O of f of n, where f of n is a function that represents the growth rate of an algorithm's time complexity. For example, if an algorithm has a time complexity of f of n, it means that the running time increases linear with the input size n. And this graph represents the big O notation. And now let us discuss about omega notation. Omega notation is used to describe the lower bound of an algorithm's time complexity. It represents the best case scenario of an algorithm, meaning that it will always take at least this amount of time to complete. For example, let's say we have an algorithm that sorts an array of n elements. The best case scenario for this algorithm would be if the array is already sorted. In this case, the algorithm would still need to compare every element in an array to ensure that it is sorted. Therefore, the lower bound of this algorithm's time complexity would be omega of n. And this graph here represents the omega notation. And now let us discuss about theta notation. Theta notation is used to describe the tight bound of an algorithm's time complexity. It represents the range of growth rates that a function can have. In other words, it describes the best and worst case scenarios for an algorithm's time complexity. For example, if we have an algorithm with a theta notation of n power 2, it means that the algorithm has a best case and worst case time complexity of O of n power 2. This means that the algorithm will take at most n power 2 operations to complete regardless of the input size. And here this graph represents the theta notation. And now let us see some common asymptotic functions. Common asymptotic functions are used to describe the time complexity of algorithms. These functions include constant, logarithmic, linear, quadratic and exponential. Constant time complexity of O of 1 means that the algorithm takes the same amount of time regardless of the input size. Logarithmic time complexity of O of log of n means that the algorithm's running time grows logarithmically with the input size. Linear time complexity O of n means that the algorithmic's running time grows linearly with the input size. Quadratic time complexity O of n power 2 means that the algorithmic's running time grows quadratically with the input size. Exponential time complexity O of 2 power n means that the algorithmic's running time grows exponentially with the input size. To better understand these concepts, let's take a look at some graphs. A graph showing constant time complexity would be a horizontal line, indicating that the algorithm takes the same amount of time regardless of the input size. A graph showing logarithmic time complexity would be a curve that starts steep but flattens out as the input size increases. A graph showing linear time complexity would be a straight line that increases steadily with the input size. A graph showing quadratic time complexity would be a curve that increases rapidly as the input size increases. Finally, a graph showing exponential time complexity would be a curve that increases very rapidly as the input size increases. And now let us discuss about best case, worst case and average case. When analyzing the time complexity of an algorithm, it's important to consider three different scenarios, that is best case, worst case and average case. The best case represents the scenario where the algorithm performs at its optimal level, while the worst case represents the scenario where the algorithm performs at its worst possible level. The average case represents the expected performance of an algorithm under normal conditions. For example, let's consider a sorting algorithm. In the best case scenario, the input array is already sorted, so the algorithm can simply iterate through the array once without making any swaps. In worst case scenario, the input array is reverse order, so that algorithm must take the maximum number of possible. The average case scenario would be somewhere in between these two extremes. And now let us see some practical applications. Asymptotic notations play a crucial role in computer science, especially when it comes to algorithm analysis, optimization and performance tuning. By using these notations, we can easily compare the efficiency of different algorithms and choose the best one for a particular task. For instance, big O notation helps us to determine the upper bound of an algorithm's time complexity, which is particularly useful when dealing with large datasets. Omega notation, on the other hand, describes the lower bound of an algorithm's time complexity, which can help us identify bottlenecks in our code. Another practical applications of asymptotic notation is in optimizing code. By analyzing the time complexity of an algorithm, we can identify areas where we can improve the performance of our code. Example, if we notice that an algorithm has a quadratic time complexity, we can find ways to reduce it to linear time complexity, which would significantly improve the speed of our program. And now let us discuss about limitations. While asymptotic notations are a powerful tool for analyzing the theoretical performance of algorithms, it's important to remember that they have limitations in real world scenarios. One major limitation is that they assume as infinite input size, which may not be the case in practice. As a result, an algorithm with a better asymptotic time complexity may not always perform better than an algorithm with a worse asymptotic time complexity on smaller inputs. Another limitation is that asymptotic notations only consider that worst case scenario, which may not be the representative of actual performance in all cases. For example, an algorithm with a high worst case time complexity may still be faster than an algorithm with a lower worst case time complexity if it performs better on average or in the best case scenario. And let us come to the conclusion of this today's topic. In conclusion, asymptotic notations are an essential tool for analyzing the time complexity of algorithms. By using big O, omega and theta notation, we can describe the upper, lower and tight bounds of an algorithm's performance respectively. We also discussed common asymptotic functions such as constant, logarithmic, linear, quadratic and exponential and how they relate to algorithmic performance. Furthermore, we explore the differences between worst case, best case, and average case time complexity and how these concepts are crucial in understanding algorithmic performance. Finally, we discussed practical applications of asymptotic notations in computer science, such as algorithmic analysis, optimization, and performance tuning. It is important to understand asymptotic notations because they allows us to make informed decisions about which algorithms to use for a given task. Analyzing the time complexity of different algorithms, we can choose efficient one of our needs. Asymptotic notations also help us identify the bottlenecks in our code and optimize it for better performance.